from the homework set, the previous homework set with difference of squares. So section 5.5 is difference of squares, and the model would look something like a perfect square minus another perfect square. And then the way you would factor that, you would have alternating signs, binomial factors that are almost identical. One's positive and one's negative. So looking at number 40, 625 is 25 squared. So this breaks down into the binomial factors 25x squared plus 1, 25x squared minus 1. Now the first factor is as simplified as it can be. Even though I have perfect squares, I'm connected by an addition, so it's finished, it's done. But the second binomial factor can be unpeeled one more layer, or it can be factored one more time. So simply copy the first one over. And now the second binomial is 5x. 5x times 5x gives me the 25x squared, plus 1 and minus 1. So you're just factoring, you're unpeeling the layers of the problem. Moving on to number 48, look at the polynomial as it's given. If there are common factors, please remove those. Reverse distributive property, factor them out. They both share a 2 and they both share an x squared. So in the homework for section 5.5, when you remove a common factor, if you have to, then what emerges should be a difference of perfect squares, which you then factor down to the next level. So here the 2x squared simply gets copied over, and I factor 25x to the 6th minus 16 plus 4 and minus 4, and then 5x cubed, 5x cubed. So my final answer is this. And I cannot break down 5x cubed minus 4 anymore, even though 4 is a perfect square. I have the subtraction. 5 is not a perfect square, and the x to the third, that is an odd number, so it's finished. It is as simplified as it can be. Okay, let's look at number 44. So number 44 can be broken down as x to the 8th plus 1 times x to the 8th minus 1. X to the 8th minus 1 can then be broken down as x to the 4th plus 1 times x to the 4th minus 1. X to the 4th minus 1 is x squared plus 1 times x squared minus 1. And then x squared minus 1 is x plus 1 times x minus 1. So your final answer would be all the factors that I'm underlining in red. That would be your final factored answer for number 44. Number 52, remove what they have in common. They both share an x to the first, and they both share a y to the second. When I remove that, I have 16x to the 4th minus y to the 4th. So just treat the double variables just like any other problem. Don't let the double variables fool you. So xy squared gets recopied. And this breaks down as 4x squared plus y squared, and then 4x squared minus y squared. So the factors in red are finished. This, however, can be broken down one more time. This is 2x plus y times 2x minus y. So everything in red represent the final answers. These are all of the factors in their prime form, meaning they have no common factors inside a set of parentheses, inside a single set of parentheses, inside a single binomial factor or a single factor. No terms are common. Number 61, getting a little bit more abstract, but it would simply be x to the 2n times y to the 2n, or x to the 2n plus y to the 2n. And then you need to recognize that what I'm underlining in blue can be broken down one more time. Now this is a very abstract application of what I'm trying to show you, but these are the C-level problems. So your final answer would be what I'm underlining in black. This factor times x to the n plus y to the n times x to the n minus y to the n. And these are your most abstract cases. And I will skip number 54 for now and go to the other side. Okay, so this was the section for perfect square trinomials, meaning your factor is a binomial times itself. Number 34, analyze or see that 3 is a common factor to each term. So before you start trying to factor and work it out, remove everything that they have in common so that you're working with a simpler problem. So when I factor a 3 out, what emerges is a perfect square trinomial. And hopefully you recognize this. The square root of 9 is 3, and 3 plus 3 is 6. Since the 6 is negative, that's my cue that this binomial factor was x minus 3 times itself. Number 40 has a typo in it, so make the 19, change that to an 18. And then number 40, 2x is common across the board. So make that an 18xy squared. So 2x is common to everyone. When I remove a 2x, then what I have left over, and again, don't let that second variable throw you off, then what I have left over is a perfect square trinomial. So copy the 2x over, and then the square root of 4x squared, or the monomial multiplied times itself to create that term, would be 2x. And then the monomial multiplied times itself to give you 9y squared would be 3y. And since your term in the middle has a negative sign, that's your cue that the binomial factors both contain a subtraction. So you could leave your final answer like this, or you could write your final answer like this. Both presentations are correct. Number 50, they have no common factors to be removed, and you can see that you've got perfect squares on both ends. So a to the fourth is the product of a squared times itself. B to the 8th is the product of b to the 4th times itself. And my term in the middle is plus. So that means my binomial factors, a squared plus b to the 4th times a squared plus b to the 4th. And you could write it as a single term or a single binomial factor raised to the power of 2. I'm going to skip number 54 for now, and I'm going to move down to number 56. So this is a very abstract problem, and it's asking you to show that this polynomial can be factored as the pair of binomials squared here. So analyzing it, you can see that they have nothing in common first, so there's nothing that you can factor out to make it a simpler problem. It's in its most simplified form as a polynomial at the moment. So you see you have a perfect square for the first term. X to the 4th is a perfect square. So x to the 4th is a product of x squared times itself. 81 is a perfect square, so it's 9 times 9. Since I have a negative sign in the middle term, that's my cue that my factors were x squared minus 9, x squared minus 9. And then going back to the other homework set, the very first night we did the homework with the difference of perfect squares, you can see, or hopefully you recognize, that both of these can be further broken down. So x squared minus 9 is really x plus 3 times x minus 3. And I have another one, x plus 3 times x minus 3. And the answer that they've presented or asked us to prove or show, they've just simply grouped the factors of x plus 3 together. And then they group the factors of x minus 3 together. And these are your very high-end abstract problems, but it does illustrate the basic property. So I'm going to ask you to bring the completed notes to class as well as the scanned textbook problems. That's all homework due for the next time we meet, and we will go back and go over the homework that was due for Friday as well.